皆さん、こんにちは。私はキングズブリと申します。ですね、アメリカのシンシナティから日本に来て、データベースの問題を話したいけど、日本に行って飛行機で、たくさん言葉を教わりました。残念ですね。そして、私は日本語で話すことのがちょっと難しいんだけど、今この話が英語で話します。ごめんなさい。じゃあ、話しましょうね。So, my name is Kyle Kingsbury. Welcome to Jepsen 10. An error runs through it. I wish I could give the whole talk in Japanese, but I'm not that good. You might know me as aphyr from the internet, and I break databases. Before I broke databases, I worked on APIs. And APIs are an interesting sort of problem because they're not like physical objects. They're more like illusions that you can look at but not touch. And they're supported by these girders, these API code instructions that we write, which are in turn founded on a VM, a language, a library, represented here by these wooden pilings, the Ruby foundations. And those pilings are in turn driven into a firm support of databases that we found lying around on the internet. And that database here is represented by a pile of tires. Now, as anybody who has worked the database knows, the pile of tires is usually on fire. Nodes are failing, the network is crashing, and it's up to us to climb the ladder of abstraction, higher and higher away from the flames, so that nobody notices that the system is down. Requests should still flow, people can still look at the rainbow, even while we're replacing components. So, if we have databases, queues, discovery services, these things strike terror into the hearts of engineers because they get into mysterious failure modes, like split brain, where two different sides of the network believe different truths. Or they can have broken foreign key relationships, where you have a reference system data, you go to look at what's being referred to, and it's not there. Or you could have transient anomalies, where you write some data, go to look for it, and it is gone. And maybe you look again later, and it's come back. These are transient anomalies. Now, we would like to know, are our systems actually safe? Are these academic constraints only, or do they occur in real-world systems? To tell this, I've been working on measuring systems in production, using a tool I've written called Jepsen. Jepsen is a software library for writing distributed systems tests. And it divides the system from the environment. It says, given a collection of clients in the outside world, let's let them interact with a system comprised of computers and networks and nodes, all of them interacting in some rich and complex way. But at the boundary between those interacting distributed parts and the environment should be some laws, some invariants that hold. I should be able to put something into a queue and then later have it come back out again. Now, the way we're going to test this is by having a collection of clients outside the system. And we'll run all the clients in the same virtual machine, the same process, so that we know exactly what each one does and when. The database itself will be running on 5 nodes, typically connected by a network. And we'll simulate the clients interacting with that system, making requests and getting responses. So we know exactly when each client makes a write and makes a read. We know exactly when and what they did, but we know nothing at all about the database itself. It's opaque. It might be in a language we can't understand. It could be closed source. It could be too complicated to think about. So I want to measure, just based on what the clients can see, did it obey the law? Was it safe? So clients will generate randomized operations, and they'll apply them to the system and see what comes out. For instance, I could put a thing into a queue, or I could try to read the current value of some cell in a spreadsheet. These are operations that I can do in a computer system. And those operations could complete in one of three ways. Either they could be okay, and we know they took place. They could fail, and we know they did not take place. Or something else could happen. We could have a crash, or perhaps a timeout. And in that case, we have to log an informational message. And we say, we just don't know what happened. Maybe the operation will take place later. Maybe it will never take place. We just don't know. So over time, we build up a concurrent history of operations. Different clients doing different things at different times. Some of them can succeed, some of them will fail. But we know what the pattern was, which things read what values, what things wrote what values. And given that history, we could write a function that looks at the history and says, is this legal? Is there some path through these operations which makes sense? Or did everything I put into the queue come out again? So that's the kind of analysis I want to perform. We're going to generate randomized operations. We're going to record a history of those operations as they were applied to the system. And then we'll verify that history is consistent with an abstract model of the system. Did it follow the rules we expected? While this is going on, we're going to get out our big network shears, and we will cut the network into pieces. We will introduce clock skew. We will kill processes. Because real distributed systems often have failure modes we can't necessarily anticipate. So, what have I found? When I started this work in 2013, with React, the default mode of last write wins would lead to lost updates. But if you use CRDTs, operations would be safe. MongoDB lost data at all levels of write concern. Redis Sentinel would go into split brain and lose all updates to one side of the network. Cassandra would have default mode of last write wins, which led to write loss. It also had a row-level isolation guarantee, saying that if you wrote two things together, they should appear together. It turned out that that was not the case. It also had a transaction system based on Paxos with two different bugs, leading it to deadlock or to lose data. NuaDB, in a famous mailing list post by its creator Jim Starkey, claimed to beat the CAP theorem by buffering all requests in RAM for the duration of a network partition. This is, of course, not actually available. It's just not doing any work. Kafka had an in-sync replica set, the collection of nodes that were up to date, which could shrink over time to only one node and then no nodes at all. If that happened, you would lose all of the records that were acknowledged on that single node, leading to lost updates. Zookeeper works, which I consider something of a personal failing, because I like to find problems. That doesn't necessarily mean Zookeeper is safe. It just means that I wasn't able to find issues in the time I had to test it. etcd and console, like Zookeeper, are consensus systems, but these two exhibited stale reads when their documentation claimed otherwise. So you could see old data from the past when you were supposed to see the most recent data. Elasticsearch in 2014 lost data in every scenario we tested. Any type of network partition would cause us to lose updates. RabbitMQ would go into split brain and lose all updates on one side of the network. Aerospike claimed to be an ACID data store, but was actually last write wins. Elasticsearch 1.5 lost data in every test case still, but this time it lost somewhat less. MongoDB, we tested again in 2015. They'd fixed the bug causing lost writes, but they had two problems with stale reads and dirty reads. You could see updates that were never supposed to be visible, and you could see updates from the past that have been overwritten by newer state. Chronos, a task scheduling system, would break forever after losing network quorum. So it would never run tests, or never run tasks again. Now I've tested a lot of things, and this list goes on a little bit. Because of translation, we're going to skip over them. But we found problems with RethinkDB, and VoltDB, and Crate.io, and CockroachDB, and MongoDB again, and Tendermint. All of these systems I have found have problems. But in this talk, I want to tell you about some new research, the things that I've been working on for the last year. Starting off with Hazelcast, at version 3.8.3. Hazelcast is an in-memory data grid, which means that it has essentially data structures that you can talk to over the network. Things like sets and locks. But when a network partition occurs, different components in the network will run independently. There is a merge function to combine information when this happens, but it doesn't always work properly. It can't guarantee that all updates will be safely preserved. There is also a split brain protection function, which is supposed to prevent nodes in the minority of a cluster from running. However, in the event of a partition, it takes time for that mechanism to kick in. So there could be an opportunity for us to observe some violation of the laws. To begin, I want to talk about locks, which are supposed to be executed by only one thread at a time. However, if you test locks in Hazelcast, you'll find that you can acquire a lock on one node, and before you release it, somebody else can go on to acquire the same lock. And somebody else could too, and someone else. So you end up with the lock being held in 4 places at once. This is the opposite of what locks are supposed to do. The queues say that you can put things in and get them out. However, if you put in 1, 2, 3, 4, you could get back 1, 1, 2, 4. No 3. So missing elements coming out of a queue is a problem. We saw roughly 2% lost. Atomic references are supposed to allow for atomic compare and set. And by that, I mean, if you have a value, and you have a transaction that reads it and writes it, it should be able to ensure that nobody else changes the value while you're changing it. So if this top transaction reads 2 and increments to get 3, it can write back 3 if and only if the value is currently 2. If another transaction does that at the same time, it should fail, because it will find out that the new value is 3, not 2. This is called compare and set. However, in Hazelcast, it says this is fine. Both transactions can commit. And now 2 plus 1 plus 1 is 3. This makes more sense if you think about the value of having split into 2 different pieces. On one node, it's become 3, and on another node, it's also become 3, but the 2 are not connected. And they could evolve independently over time. So I could read 3, then 5, then 3, then 5, depending on what node I talk to. At the end of this process, the nodes will come back together, and they'll choose a value, but it can't guarantee which one it picks. So maybe your number goes backwards, even though you've only counted up. I mean, what are you doing? Look at your life, look at your choices. Nobody wants an atomic reference which is not actually atomic. So you say, okay, let's try ID generators. Can I generate unique numbers? No. In fact, out of 30 seconds of ID generation, I could get 91,000 duplicate IDs out of 834,000 generated. Because it's based on that same algorithm. Maps have put-if-absent functions and replace functions, which aren't even well defined because the value of the map could change over time. What does it mean to replace a value if the map has 2 different values at once? It's not a well-defined operation. So of course, these things lose data, even with quorum protection, even with all the safety measures turned on. However, if you use a custom merge function written in Java, you can build safe CRDTs. That will be eventually consistent and preserve updates. I have a few recommendations for engineers building these kinds of systems. If you're going to use a data type or provide a data type, choose an algorithm which is appropriate for it. If your algorithm is to generate unique identifiers, use flake IDs. If you need to have a counter system, use a PN counter, which can count up on each node independently. If you need to have a linear order of computation, use something like Paxos or Raft. Don't just make up an eventually consistent algorithm and hope things will work. If you're a Hazelcast user, it's perfectly okay to use it as a cache, and that's how most people do. However, some people, including partners listed prominently on their blog, don't use it as a cache. BaggeryDB, for example, uses it to generate transaction identifiers using the unique ID generator. So that means it could generate 2 transactions with the same ID. What happens when that occurs? I'm not sure, but I'm a little bit concerned. OrientDB has similar problems. It uses Hazelcast to set up its initial cluster state. Finally, distributed locks are not real. Anybody who says that you can acquire a lock on one node in a distributed system, do some work, and then release the lock, and that will be exclusive, is lying to you. I don't have time to talk about this in detail, but see Google's Chubby paper for more explanation. I want to talk about Aerospike at 39903. Aerospike is a distributed and sharded document store, which means it's a key value store where the documents or the values have some structure, some little internal fields. In version 3.5.4, which we tested 2 years ago, it went into split brain, and some parts would preserve data and some parts would lose data. You could have lost updates, stale reads, dirty reads. But they went back to the drawing board and redesigned the system. And in version 4.0, they're releasing a new safety mechanism called strong consistency, which offers linearizable updates. They do this using a custom consensus protocol, which is normally a bit dodgy, but in their case, they wanted to be able to offer consensus with only 2 nodes and tolerate node failures only some of the time. It's a long story. The other thing they did was fix many bugs which led to the loss of data in the eventually consistent mode. Doesn't prevent data loss altogether, but it reduces the probability so that the system loses data less often. And it turns out that many use cases only need probabilistic correctness. For example, machine learning models. If you can get enough of the data, then you can make a good enough guess. But if you lose half of it, your guess is not very good. The first thing we found with Aerospike is that you would start a test, and the very first thing that would happen is you would read 2. It's sort of like you purchase a new refrigerator, and you open the door, and inside is a carton of milk. You look at this going, where did this milk come from? Doshite. And it turns out that if you look at the full history, before you did the read, there was a write of 2, but the write failed. It should not have taken place. They just said, oh, no, I did not write 2, but it really did. This occurs because when a client writes to the server, when a client writes to the server may not own the data, so it proxies to a remote node. That remote node could apply the write, so a value of 2 is written. But the response could be lost. And if it's lost, then the server in the middle will retry. It makes the request again, and then the remote server could reject it because maybe conditions have changed, it no longer owns the data. That rejection is passed back to the client, which says, operation failed, did not take place. So we can convert a successful operation to a failing one. We've seen this problem in several databases so far. It is important to always check to see that you choose the most indeterminate result, not necessarily the most recent result. Now this is fixed in 3915. Hooray! So we went on to test node crashes. We would drop pianos on nodes that are walking about their days. And we found something interesting. If you kill one node out of 5, things are okay. 2 out of 5, okay. 3 out of 5, everything stops. This is normal. Most consensus systems work with majority quorums. So if you have most of the computers alive and talking to each other, they can still make progress. However, when you restarted the nodes, it would never run again. And this is unusual. You usually expect that when you restart things, they start working again. The reason for this is somewhat tricky. It's because AerorSpike isn't actually designed to suffer concurrent crashes of nodes. Now there's an administrative command, so you can swoop in and shout, "Heroes never die," and resurrect the partition. However, partitions that you bring back may be a little bit not all there. There could be some data missing. The reason for this is that AerorSpike did not flush writes to the disk before acknowledging them to other servers. In a new version of 3921, they've added an option that makes sure it writes things to disk before it says it's got them. And that means that AerorSpike can now, if you use that option, survive the crash of concurrent nodes. Now clock skew can also lead to lost updates in AerorSpike. Keys in AerorSpike don't just point to values. They point to some metadata. And that metadata includes a clock that's supposed to tell you what the most recent version of a data record is. That clock is made up of 3 pieces. There's a regime, which is incremented for every new leader. And then there's a wall clock that advances monotonically for that particular leader node. And if you ever have to do 2 things in the same wall clock, then you have a counter that will increment further. So this gives us a total order of operations. You get a clock and you can compare by regime, who's the newest leader. On that leader, which one was the most recent clock? In the same wall clock millisecond, which was the most recent operation? You can always tell. Very good. However, for performance reasons, that entire data structure has to fit inside of a cache line. And cache lines are relatively small. And with all the other data, there's only 6 bits left for the regime. So you can do 64 elections, and then you can't do any more. Because if you did, you would go from 63 to 0, and you couldn't compare regimes anymore. So what do? So what you do instead is you let the regime overflow. However, you look at the number of overflows that could happen. It's going to take at least 27 seconds, because of timeouts, for you to overflow that number. So if 2 wall clocks are more than 27 seconds apart, then you compare based on wall clock, because you might have overflowed. If they're less than 27 seconds apart, then you go by regime. This allows the following series of events. Node A, a leader, receives a write, W1, and it pauses. Node B is elected a new leader with regime 2 and processes a write, W2. So it says my value is 2 at regime 2 and time 0. 27 seconds pass, and node A wakes up and says, I have a write. Let's process W1. My value is 1, my regime is 1, and my time is 27 seconds. Well, I'm going to broadcast that to node B. And B says, ダメだよ. I am the newer leader. I have 2 and you're from regime 1, so I will not accept this right. The client discovers the right has failed. This is good. However, later, the 2 nodes will check with each other to reconcile their data. And this time around, they compare based on wall clock, and they say, node A's clock is 27, node B's clock is 0, so B must be out of date. Let's prefer node A's illegal write of 1. So we destroy the successful write of W2, and we preserve the failed write of W1. コンピューターは大変ですね. I mean, really, right in front of my salad. So, both clock skew and not using fsync were known failure modes in Aerospike. They were trade-offs that the designers made intentionally. As long as you stay in the clock skew bounds and you use durable writes, then it looks like Aerospike is now linearizable, which is a really big improvement from last time. I'm very happy. Keep in mind that cross-data center replication, scans, user-defined functions, these things don't yet go through the strong consistency mechanism. It's stuff that they'll work on in the future. Finally, I'd like to talk to you about dgraph at version 102, which has this adorable mascot. Dgraph is a graph database, and the way it views a graph is a collection of relationships between entity and a value and some named attribute that connects them. So if I am an entity, then my name attribute could be the value Kyle. And values could also be other entities. So I could have a friend attribute that points to Rita-san. If I have a collection of these relationships, I can build up a directed, labeled multi-graph. And that's the data structure that dgraph maintains. And changes on this data structure are supposed to be snapshot isolated, which means that if you do a transaction, all of your changes should occur in isolation. Nobody else sees them. So I hold my cards close, do all my work. And then, when I'm ready to commit, I lay my cards on the table, and they say, did I change anything that somebody else changed while I was doing my transaction? If no, then I can commit. But if something else changed, then I have to abort. I can't make my commit anymore. In addition, dgraph offers a number of claims around monotonicity. It claims linearizability in some places and something like sequential consistency in others. Not quite clear. The way it provides this is with a control system called Zero. It's a raft cluster which is responsible for checking transactions to make sure that they don't conflict, and also for allocating attributes to different shards. Each shard runs on a collection of alpha nodes, which are responsible for storing the data. So maybe all of the friendships live on one particular alpha shard, and all of the names and ages live on a different one. Now, in the system, we found 23 issues. I don't have time to talk about all of them today, but I want to show you a few highlights. So in join issues, when you first start up the cluster, we found problems like bug 2137, where when a node starts up, it looks to see if it has any peers. It says, somebody else is in the cluster with me. Who's the current leader? I would like a copy of their state. And so it will try to fetch that data from the leader. But if two people come up simultaneously, then they look at each other and say, you're not the leader, you're not the leader. Let's try again. As a result, they never get done looking for leaders and never get to the place where you could do leader election. They're just back and forth, back and forth. Bug 2138 was where a join request would arrive on a node that had just started up. And it would look at some internal state about the cluster, which it had not yet initialized. The default values were null, and it would dereference that null pointer. In a language like Java, this would be an exception. But in the Go language, which is what dgraph uses, it causes the entire process to segfault. So the node would crash. Both of these are fixed in 104. We found a couple of cute floating point bugs. Floating point, bane of programmers' existence, causes things like this to happen. You set the age of a person to 3. And the computer says, 3. I'm going to parse that value with Jepsen. It's 3.0, because all Jepsen numbers are floats, right? It then says, well, because this is a floating point number, and I've never seen an age before, all ages are floating point. And if you go to ask it for the age again, it says 3.0. This is not so bad, because usually ages are floating point. They're small numbers, they're continuous, this is fine. But certain numbers aren't exactly representable in floating point. So if you set blah 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 426, what you get back could be blah 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 000.0. Not the same number. Okay, JavaScript does this. Let's try setting an integer schema to prevent it from coercing things to floats. Right? 2378 shows that the number 3 gets parsed as Jepsen, it reads 3.0, and then it converts it back to an integer, and then puts it into the storage system. So you put in 3 and you get back 3, but if you put a number like blah 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 995, you get back blah 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 996 instead. Not the same number. And in extreme cases, this can do something really weird. On the top, we have the integers, signed integers from -2 to the 63rd to 2 to the 63rd minus 1. The bottom line is floating point, much bigger space of integers, but not every integer is representable. So once you get above 2 to the 53rd, it's like every other number, and then every 4th number, right? So you put in a big number, like 2 to the 63rd minus 5. It gets converted to 2 to the 63rd, because that's the closest possible floating point number. And then the integer schema says, but this was supposed to be an int. Let's convert it back. So the closest number to that is 2 to the 63rd exactly, which is a 1 followed by 63 zeros, which is -2 to the 63rd in integer representation. So you put in a number like 922 blah 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 296, and you get back -922 blah 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 808 instead, the wrong number of a completely different sign. That's fixed in 106. We found a number of crashes and lockups in dgraph. For instance, cases where every transaction would fail for hours on end, with errors like read timestamp X less than minimum timestamp Y. Looking at this, like, the timestamps are advancing. Each time the read timestamp goes up by 1 for every transaction it executes. So if you wait long enough, it will catch up. But it could take a long time. Why is this? Well, the 0 nodes, the control system, are supposed to tell all the alpha nodes whenever there's a change in leadership. So it says, there's been a new election. 0 node C is now the current leader. Talk to node C if you need a timestamp. So if there's a series of elections, like node A and node B, then the alpha nodes should follow along and get A then B. Maybe they're a little bit out of date, but eventually they'll catch up and know the current leader. Right? Well, not quite, because this leader information was transmitted in a Go routine. And the go routine could pause. So the A go routine could take longer than the B go routine. And then the alpha node learns B then A. And until a new leader election happens, those alpha nodes will continue using the outdated leader and getting old timestamps that won't work on the new leaders. So you're stuck. Duplicate upserts. An upsert is a procedure where you want to create only one copy of some record. For instance, I want to have people identified by a name, and I don't want two people to have the same name in my collection. So I do this in dgraph by saying, is there currently any user named, say, Felicity? And if there is, then I abort the transaction, because I don't want to create two copies. But if there's no current Felicity, then I go ahead and insert person with name Felicity and age, say, 83. In an SQL system, you would have a uniqueness constraint, like an index on this value instead. But dgraph doesn't do that. It actually uses snapshot isolation and a check on the index to make sure that two different transactions doing upsert won't collide. At least in theory. What actually happens is that you have 3 or 4, 10 transactions, each one of which says, oh, there's no current Felicity. All of them go to insert. And the transaction manager says, this seems fine. All of you get to insert. So you query for Felicity, and you get back 3 copies, all of whom say, hi, I'm Felicity. A decidedly unfelicitous result. The reason for this is because when a node goes to commit a record, it's supposed to send a little message, like a form, to the transaction coordinator. And it says, please commit my transaction. Here's all the things I changed. It should say, I changed the name Felicity, so that 2 transactions that both changed it could have a conflict and one could abort. However, they forgot to fill out the form. So it would send a transaction message saying, commit this. I changed nothing at all. And the transaction manager says, great, go right ahead. Everybody gets to commit. That was bug 2149, now fixed in 104. We found a number of consistency violations, most of which were in something called the bank test. In this, we simulate a really tiny bank, which has accounts identified by number and corresponding values. So account 1 could have 50 yen, account 2 could have 20 yen, account 3 could have 30 yen. And we can move money back and forth between accounts by subtracting and adding that amount in a transaction. The laws of snapshot isolation say that we should never create or destroy money. The total should always be constant. And you should always observe a snapshot of the system. So you should always observe the same total, no matter when you execute. So if we move 30 from account 3 to account 2, we should see 50-50 afterwards. Unfortunately, you can actually see things like this. Node A has, number 1 has 50, account 2 has 50, which is the value after the transaction, and account 3 has 30, which is the value before the transaction. We're seeing like a split moment in time. It's called read skew. So that leads us to have incorrect totals. And if we write that value back into the database, because we're doing a transfer based on it, then the total of the accounts over time could fluctuate up or down. Worse yet, we found bugs where you would query the current amount in an account, and it would have a nil amount, or a missing number. This is really bad because we never ever create accounts without a number or without a value. Those things should always be present. So this suggests there's something very broken inside of perhaps the indexing system, but we're not sure. If you graph the total balance of accounts over time, you could see that things stay at 100 for a while. But then something occurs, and you end up with most of the value disappearing, or maybe new values introduced suddenly. Weirder yet, you could have scenarios where some of the time you see, say, 50, and some of the time you see 70, 51, 69, 50, 82. It's like two separate tracks are evolving independently. It looks a little bit like a split brain, but it turns out that it happens on every node at once, which is very perplexing. We still don't know what causes this, but we think it might be related to predicate migration. Finally, we have cases of lost inserts. So you would ask dgraph, all right, let's not try for snapshot isolation. That's a bit tricky. Let's just try to put in a bunch of numbers and make sure we can read them out again. No conflict ever. So you insert 1, insert 2, insert 3, and dgraph says, okay, okay, okay. You insert 50,000 records, all of which succeeded, and you ask dgraph, show me what you got. Dgraph says, I have one element and it is 50,000. What? What about 30,000? What about 2? What about all those other numbers you just said you got? Where are they? Well, this happens because when dgraph moves data from one node to another, it builds up a serialization data structure. And it populates it by looping over all the data in a big block of records and setting the serialization structure's key based on that loop. And it does this with a mutable loop variable, a pointer. So you get a serialization structure with 50,000 copies of the same pointer, all of which point to the final key, 50,000. Because of that, you end up copying only one record. All the other ones are sort of duplicates of it. So you could destroy almost all the updates. This was fixed in 105. If you are using dgraph, I recommend you upgrade to 106 or higher. It fixes many of these bugs. You should also use the upsert directive to make sure that it checks for conflicts whenever you're doing upsert transactions. That used to be the default behavior, but as of, I think, 103, it is no longer the default. Finally, we didn't have time to talk about this in detail, but there's both client-side and server-side sequencing in dgraph, which are the ways that it makes sure clients see a sequential order of transactions. The server-side sequencing mechanism is new. They introduced it during our collaboration, and it's probably going to take over from client-side. By asking the server to enforce an order, it's often safer than having the client guess. Be advised that as of 106, dgraph still loses data in healthy clusters. Out of the 23 issues we found, there are still 4 outstanding, but they're working on fixing them, and hopefully it will be better. There are some lessons, I think, for database authors here. One of them is that even if you use a correct algorithm like Raft, it's not necessarily a guarantee that you've used the algorithm correctly. So Raft in dgraph provided a total order of operations, 1, 2, 3, 4. But dgraph would take those operations and execute them concurrently in Go routines, which meant that you could execute 1, 2, 3 on one node, and 3, 2, 1 on a different node. And then they come to different states. Now, there were mechanisms that were supposed to make this safe, but they didn't always work correctly. So it can be a little bit tricky if you're trying to work around the way that the system was meant to behave. Watch out for async reordering in general. Several of the problems we found in dgraph had to do with coroutines, executing some code later than they were supposed to or earlier than they were supposed to. So whenever you do this, yes, it's nice for performance. Yes, it's nice for letting you escape deadlock some of the time, but you have to be prepared for non-determinism. Be careful with uninitialized state. When you're going to get a message, make sure you're ready to process it. Don't just try and dereference null pointers immediately. You can use locks, or you can have default values, however you'd like to do it. Use reconciliation loops. If you need to go from one state to another, have a method that gets you a little bit closer. Look at where you are, try to move one step closer each time. This is often more robust than trying to execute a series of steps in sequence, because if one of the steps fails, then the rest of the sequence could be broken. Don't just assume that leaders are actually authoritative. Many distributed systems we've tested have this problem. They send a message to a node thinking, you're probably the leader. And by the time the node receives it, says, I'm not the leader, what are you doing? Or a node takes action thinking it's the current leader when some other leader has already become more recent. To recap, when you are a database engineer and you're choosing a database to run in your system, you're sort of like Ariel, the mermaid, and the vendor is sort of like Ursula, the sea witch. They're going to give you this long set of documentation, and if you don't read all of the fine print, you could end up surprised. Perhaps you have to kiss the prince by the third day, or else your data is forfeit. It's important to look for these things. Then, throw away the documentation and try it for yourself. Because sometimes the vendors don't necessarily know what the system does during a failure. Look out for phrases like strict consistency, strong, acid. These things are weasel words. They sound nice, but they're not necessarily a strong guarantee. I want to encourage both users and vendors to be formal and to be specific in the guarantees that they expect and provide. Because not every system has to be 100% safe. Sometimes some data loss is actually okay. Other times, you need a strict order of transactions, or you need to know what happened right now. So these different types of programs will run on different types of distributed systems. There's no one size fits all. It's not enough to test in the happy case. We need to look at failures too. So test your failure modes, like process crashes. Try Q-9 and see what your database does. Try node failures. Use AWS Terminate or turn the power off on your computer. That might introduce a new behavior. Try clock skew. Real-world clocks can skew by tens of seconds. If you've ever run an AWS, you probably know this to be true. So use the date command to set the date into the future. Or use libfake-time to lie about the date to a particular process. Look for garbage collection and I/O pauses. You can simulate these with sigstop and sigcontinue, and they look a lot like network partitions because they pause the flow of information in and out of a program. Finally, network partitions are a really powerful tool. Simulate them with iptables-j drop or with TC to get probabilistic loss of packets. It's not enough to test our systems individually, because the composition of distributed systems is still an open research problem. We don't know the laws for gluing together two different types of guarantees. So while I've talked about individual databases, because I'm trying to do research for everybody, when you're building a system in production, you'll want to think about the way that your API makes calls to the database, and about the cache, and about the queue, the way these things interact. Try to measure the whole system. If you look for perfection, you'll never be satisfied. Every one of these databases will fail in different ways. But if we do a little bit of work, we can make our systems significantly safer. And to do that, I think you want to use property-based testing with high-level invariance. So apply random operations, see what happens, make sure that the laws you expect actually hold. And test these things with distributed systems failure modes, because it's not enough to look at the happy case. This work would not have been possible without the help of Hazelcast and community members Jordan Halterman, Luigi Dell'Aquila, Luca Garuli, and Denis Sokoroslov. Aerospike and dgraph funded their research, and Peter Alvaro from UC Santa Cruz has provided invaluable advice. You can read more about this work on Jepsen.io. I thank you very much for your time, and I will be happy to take any questions.
9名タイムに入りますけども、質問のある方、挙手をお願いいたします。Do you have any question? 真ん中の、紺色の T シャツですか？
ちょっと
翻訳は
So, to repeat the question, here in Japan you're deploying large-scale distributed systems, and you are concerned about the latency between nodes being high. Are there any things that I found specifically with respect to high latencies? In my research, I introduced very large latencies just to find problems. But in production, you'll find, better? Oh, okay. Okay. Better. So, yes, when I test, I introduce very large latencies, specifically to find problems. And I think you'll find in production systems, when there are high latencies, you are forced to make more aggressive trade-offs to avoid consistency errors. Either you have to pay very long wait times, or you can run quickly, but sacrifice some consistency. That's one of the implications of the cap theorem. But as far as the safety testing work goes, my results apply to both small and big latencies. Does that help?
その中で、高遅延だった場合に、どのような問題が出たのか、代表的なケースがあったら教えていただきたいです。
Are there any bad impacts of high latency tests? All of my tests involve latency on the order of tens to 60 seconds. So all of these do involve high latency. Some of them happen even in short latency cases, but I usually make it large to make it easier to see the problems.
OK。もし後でお時間あったら、ちょっと質問させてください。ありがとうございます。
Of course. Thank you.
はい。他に質問がある方、先頭の方。
So you mentioned for all the generation of operations that are all done randomly. Have you done any research into perhaps exploring the operation space or operations more intelligently than pure randomness, and what do you find?
Yes. So one of the things that Peter Alvaro is working on is designing a series of failures specifically to stress the system and guessing where your failures are likely to be most interesting. I also design the schedules. They're not always purely random. Oftentimes I know a certain series of events will be more likely to cause problems. So I apply some human intelligence to that, but it's mostly based on intuition. It would be nice if we could do like some sort of fuzzing or code analysis and be able to guess, but not always the case.
はい。はい。
So first off, I want to thank you for doing all this work. It's extremely valuable. Nobody else is doing it. I find that interesting. So I wanted to thank you for that. And also, I think that a lot of these databases can be trade-offs. They essentially try to make things a little bit more performant at the cost of consistency and these type of bugs. Do you see a lot of any particular trends in terms of the way that they choose their defaults, their settings, and what sort of implications that allow databases have for allow databases when you change the defaults to something that's more safe, but perhaps less performant? Do some of the databases just get totally unusable when they're in safe mode? That sort of thing.
Yes. So I think database vendors are treating the problem more seriously now. They're choosing safer defaults. Systems like VoltDB, for example, actually opted to make their system, in some cases, twice as slow in order to offer linearizability by default. I think that's an admirable choice, but it's not necessarily common. A lot of people still opt for stale reads or even read uncommitted by default. And anecdotally, many companies say, oh, we're not willing to run with stronger versions, it's just too slow. But I don't have a lot of quantitative evidence I can show for that.
はい。他に質問がある方いらっしゃいますでしょうか。右側の通路の前段にいらっしゃる。3段目にいらっしゃるからです。
So for testing systems like Dynamo, two of the systems I talked about, the React Extender, are based on the Dynamo paper. But DynamoDB as a hosted service, I can't test. Sorry, I can't test because I have no access to control it. I need to be able to introduce failures, and Amazon doesn't have an API that will let me do that yet. So unfortunately, if you want to test these systems, you'll just have to watch and hope that a failure happens, which isn't going to be as good as being able to use the failures yourself.
はい、時間になりましたので、以上で拍手を終わります。もう一度盛大な拍手をお願いいたします。